Welcome back to the Math Professors. This YouTube channel covers topics that can be found in any college math class, so if you like free content, please consider liking, subscribing, and sharing. So the question comes with this is, does this have two unique antiderivatives? And the reason why I ask this is because I can set this up by doing this by parts, where I can do two different by-part substitutions, and it looks like it has two different answers, and then we're going to look at it and see, are those two answers unique? So let's get into it. So let's start out with the original setup, so the secant squared of x times the tangent of x dx. And I also want to write this as the integral of the secant of x times the secant of x tangent of x dx. Okay, so I've set up in this form. What we need is a function that is differentiable and a function that is integrable. So I know the derivative of the tangent, and I know the antiderivative of the secant squared. So the du, or its differential for tangent, is going to be equal to the secant squared of x dx. And then the antiderivative for the secant squared is going to be equal to the tangent of x. So then when I set this up, uv, this is going to be the tangent squared of x, u times v, tangent, minus the integral of v du, so minus the integral of the tangent times the secant squared of x, which is really the exact same expression. So the secant squared of x times the tangent of x dx. So now what I know is this looks like it's going to be one of those repeated integrals. So this is equal to that target integral I, let's say that. So I have I is equal to this thing. Well, this is also I. So when I send this to the other side, I'm going to have two of these target integrals is going to be equal to this tangent squared of x. So that means I is going to be equal to the tangent squared of x, all divided by 2 plus c. All right, so let's see what we have for the other one. So what if I integrate this one by parts, and let's say u, again we need something that's differentiable. I know the derivative of the secant of x, and I know the antiderivative of the secant tangent of x, so dv is going to be equal to the secant of x tangent of x dx. So the derivative of the secant, du, differential, is going to be equal to the secant of x tangent of x dx, and the antiderivative of the secant tangent is going to be equal to the secant of x. So then again, the target integral I is going to be u times v, so we're going to have the secant squared of x minus the integral of v du, which is again going to be equal to the secant squared times the tangent of x. So then again, I have another I here, so sending the I to the other side, I have 2I is going to be equal to the secant squared of x. So that means I, our target integral, is going to be equal to the secant squared of x all over 2 plus c. So this is kind of where we ask, are these unique? So what we know is they're not unique. They look similar, but they're not the same. So what we're going to do is we're going to look at the Pythagorean theorem that says, if you don't recognize it, everybody recognizes this one: sine squared of x plus cosine squared of x is equal to 1. So what I want to do is let's go ahead and pull out a tangent squared. So if I divide everything by cosine squared of x, this says that the tangent squared of x plus 1 is equal to the secant squared of x. So what I can do is I can rewrite this, let's rewrite the secant since it's already isolated. So I can rewrite the secant squared of x as the tangent squared of x plus 1. And this is still all going to be over, this is all going to be, over 2 plus c. So now I'm simplifying this expression. This is going to be equal to the tangent squared of x over 2 all over 2 plus 1/2 plus c. And what we know is that c represents any constant. So really this 1/2 plus c still represents a general C. So these are not unique. You actually get the same answer using two different substitutions. And that's all I have for you today. So again, please consider liking, subscribing, and sharing.